we're going to talk about then the periodic table, physical versus chemical change, what elements are. We kind of learned that. And then we review atomic structure, what's inside of an atom. And we review how to draw Bohr-Rutherford diagrams. And then that relates to electron arrangement. So basically, this whole period is a really condensed review of grade 9 chemistry. In grade 10 science in Canada, you don't need to remember grade 9 science, except when it comes to chemistry. Okay, notice that in biology, we talked about cells, tissues, plants, none of which were mentioned in grade 9. And in physics, in the next unit, we're going to talk about light. We learned about electricity in grade 9. Not really related here. So, but in chemistry, you do need a working knowledge of last year. So this is what this lesson is about. All right, so in the chat, describe this using a word. And I'm looking for different descriptions here, so let's go. What do you come up with? First of all, that's a gold bar. Sorry?
I want a gold bar.
You want a gold bar. So do I, actually. If I had a gold bar, yeah, I wouldn't say I'd retire. I would care a lot less about my job. Okay, shiny, robust, yellow, ductile, and malleable. Okay, those are excellent words. Okay, any other words before I just show you some? Metallic, that's a good one. Tasty? No?
Pretty.
Pretty, expensive, okay. All right, so here are some words that I came up with. A lot of you gave me like pretty, expensive. Those are describing its value, not describing its physical appearance. I guess pretty is one thing, but again, that's subjective. These things that I showed you are some of the properties of the gold bar itself. Shiny, people said that. Yellow, people said that. And the rest of them I didn't see because it's a mix of physical and chemical properties. Did somebody say hard? Because a robust, that's the same thing as hard. Smooth, nobody mentioned. Non-flammable, definitely no one mentioned that. Heavy. If you ever hold a gold bar, I don't know if you have. If you have, though, you can know that this is actually really heavy. If you go to the Canadian Mint in Ottawa, if you ever go to Ottawa, I suggest you pay a visit. Inside the Canadian Mint, well, that's the plant where we print coins. There is a gold bar about the size of a laptop, a small laptop. I tried to lift it with one hand. It's chained to the desk, and there's this really big dude standing right next to that gold bar. I'm pretty tall. I'm 6'3". That guy's taller than me, probably twice my weight too. So he's just watching you. I tried to lift that gold bar with one hand because I thought, how heavy can this be? I couldn't do it. So I had to use two hands, and boy, was that heavy. I'm telling you, I don't think that guy needs to be there. If I'm holding that, I'm not going to run very fast. So gold is very heavy because it's a heavy atom. Smooth, unreactive, so gold doesn't really change. That's why you can buy gold, just store it somewhere, you come back, it's still there. If you buy something else, buy ice, put it somewhere, you come back, it could have melted. You see what I mean? So these are some properties of gold. Some of them physical, others chemical. So we need to know the difference between physical properties and chemical properties. So what's the difference? Well, physical, if you're physical, then you're describing this thing without referencing it turning into another thing. Okay, what do I mean? So color, I'm talking about gold, it's yellow. Well, that's it, it's just it. Gold is yellow. Texture is smooth, it's dense, it doesn't really smell like anything. It does not dissolve in water. If you lick it, it doesn't taste like anything, and it has a really relatively high melting point. These talk about gold, and even if you do all of these things to it, it's still gold. Okay, you want to measure how heavy it is. I mean, you don't change the fact that it is gold, just put it on a scale. Chemical properties are descriptions that, if you want to test it, you would change it into something different. For example, flammability. How easily does it burn? Well, to find out, you're going to have to burn it. If you burn it, it's not gold anymore. It's gold oxide. Okay, and how badly does it bleach? Well, if you bleach it, it's not just gold anymore. It's bleached gold, which is something different. Okay, if you corrode something, like corrode iron, it's not iron anymore. It's rust. It's something completely different with different properties, different appearances. So chemical properties refer to its ability to change. Okay, does that make sense? So physical, just think, well, physically. Chemical is you burn it in the lab, you do some experiments with it, with chemicals, and what happens to it. Okay, so new substances are formed with chemical reactions. So if you're going to study the chemical properties, you're going to have to change it into something else. So this brings us to physical versus chemical change. A physical change is something that doesn't produce a new substance. After the change, it is still what it is. Okay, whereas a chemical change, after you change it, now it becomes something new. So let's go through this. The first one, the karate chop. If you break bricks, is that a physical or chemical change? Either in the chat or into the mic.
Physical.
Okay. Physical. A lot of people are saying physical. You sure? I mean, broken bricks, are they still bricks? Sure. Broken bricks are bricks, they're just broken. Okay, so that's physical. Okay, that one's quite easy. Okay, chopping fruits and vegetables. Physical or chemical? Okay, also physical. Okay, physical. Again, yeah, chopped fruit or chopped vegetable, you didn't change the fact that it's still vegetable. You chopped up some tomato, it's still tomatoes. So that's physical. How about boiling water? Okay, now I'm getting some chemical. Any other answers? Chemical. So unanimously, you guys are saying that this is chemical. Oh, Burke says it's physical. Okay, so I'm getting now physical. So now we have a debate. Why do you guys say it's chemical? Like, anyone want to back up their answers? It's changing state. So okay, so you're saying that it changed. It's not water anymore. It's water vapor. It's a gas now. Okay, I get what you're saying. Why is it physical? Those that answered physical. Do you want to back it up? It doesn't change the structure. Okay, that's a good argument. Water vapor is still water. It's H2O. It's just that it's floating in the air now. So the answer is physical. So this second logic is correct. Even if you change its state, we call it something different, it doesn't change the fact that this is still made up of the same thing. Okay, liquid water versus water vapor, they're both H2O. It's just how close are the H2O to each other. Even solid water, we call it ice. We have a different word for that. But that is still water in the solid form. Okay, so these are physical properties, physical changes, boiling, freezing, because you're not changing the fact that this is water. Okay, so what about the bottom left, rotting apples? Which one is that? Okay, chemical. Any other answers? You guys concur? Okay, so unanimously, this is chemical. You're right, this is chemical. Now, here's the difference. If an apple rots, it's not the same thing anymore. It smells different. It looks different. It tastes different. It behaves differently. So it is now something different. Something happened to it. The flesh reacted with something to become something else. You wouldn't eat that, okay? Eating an apple is considered to be healthy. Eating rotting apples, that's not healthy at all. So it has different effects on your body as well. So that's different, okay? Chemical. Grilling stuff on a barbecue, burning something, or cooking food, scrambling eggs. Okay, chemical, right. If you cook food, something changes about the food. The color, the taste, the smell, the texture. In fact, that's the whole idea of cooking the food. You want to change it. So yeah, that's chemical. And usually, not always, usually chemical changes are irreversible. Okay, you cannot unrot an apple. You cannot uncook an egg. Lastly, Elsa. What is that? I'm talking about her ability to freeze stuff. Physical. And I think I gave you the answer to that one. Well, in her case, it's magical, but really magic is just unexplained science. So, and she's probably just lowering the temperature and freezing stuff. That would be physical, turning water into ice or snow. How do I unslice an apple? Okay, good point. I see what you're saying. Physical things, like if you break something like a brick or slice an apple, you can't really attach it back. You see what I mean? Yeah, but how do I explain that? You kind of can. For example, in the case of a brick, you can still melt it and remake that brick. For apples, for fruits, it's different because they're made up of cells, but you can reattach a limb and that will grow back. Apples, yeah, they wouldn't unslice, but still, the fact that it's still an apple is physical. Okay, does that make sense? Glue it. Yeah, I don't think gluing the apple is productive. Okay, so how do you know if chemical changes occurred? Well, here are some evidences that will tell you, hey, if I see these, it's probably chemical. Okay, so your first cue is that something changes color. If you mix very often in chemistry, you mix two things together, something new is formed. And sometimes it has a color change and it's quite pretty. If you mix this yellow liquid with this colorless liquid, wait, it turns red, that's awesome. Well, that's a chemical reaction. Okay, and also if the thing feels warmer than before, or it's producing light, it's also chemical. Okay, I'm not saying you basically put it over like a stove. That's different. That's physical. I'm saying that in a chemical reaction, you mix two test tubes together. Something is happening, and then you feel the test tube. Now it's becoming warmer and warmer, and you didn't put it over a source of heat. It is generating the heat itself. That's chemical. Okay, chemical reactions can generate heat, or it can absorb heat and make it colder, and also produce light. So fireflies, they actually have a chemical reaction in their gut to produce light. Okay, so that's chemical. If you produce a gas where there wasn't one before, again, I'm not talking about heating it like water boiling. That's different. I'm saying that I'm not changing the temperature. I'm simply mixing two things and it starts bubbling. That is evidence of a gas being formed, and that would be chemical. Same thing, a precipitate. Yeah, English is an awful language. The word precipitate has many meanings. One means rain and snow. The other is in chemistry. Precipitate means the thing that appears as a solid if you mix two solutions together. Okay, so if you mix two things, they're both liquidy, you kind of mix them, and then this cloudy, solidy substance come out. That's the precipitate. Okay, and that is chemical because it wasn't there before. Now it's here. Something new was formed. And also, not always. Okay, in grade 10, we're going to say, yeah, pretty much always. Change is irreversible. If you have a chemical reaction, it doesn't go back. Like boiling an egg. That statement is false, by the way. Some reactions can go back. It depends on the reaction. But for all intents and purposes for this class, it doesn't go back. Okay, so these are the evidences of chemical change. And usually in a chemical reaction, more than one of these occur. Okay, so you can definitively say, hey, something new is happening. That's chemical, not physical. Okay, any questions about that? The difference between chemical versus physical. Okay, so let's now talk about the periodic table. I didn't give you one this year because I didn't see you. I don't know if I have already. I should post one on Google Classroom. If I haven't done so, I will. I think I did, but I have a terrible memory. So you need to download that periodic table and have it with you. Okay, you can use that for your test, quizzes, whatever. Okay, so let's define some terms. An element. An element is something that you can find on the periodic table. Okay, the periodic table is a list of naturally occurring or synthetically made pure substances. Okay, you cannot break it down any further. You can break things down by cutting it and cutting it and cutting it until you reach the element. Then you can't slice it anymore because you're at individual atoms. And those atoms, the different types of atoms, are in the periodic table and they're elements. Okay, so how do you know if something is an element? You look on the periodic table. If you find it, it's an element. If you don't see it, it is not an element. Okay, copper is on the periodic table, is an element. Bronze is not on the periodic table. It is not an element. It's a mixture of different metals to make bronze. Does that make sense? So please know what an element is and how to find it. And of course, the periodic table is just the group of all the elements that we have discovered so far. And this is from a textbook. And those textbooks are old. If you see the bottom right corner, you see a lot of three-letter triplet elements like UUB, UUT, UUQ. Yeah, those have been replaced with their modern names. Back when the textbook was printed, they didn't have names, so they just had weird Latin symbols for names. But now they actually have names. And in the classroom, if we ever go back to the classroom, you're going to see that I have a periodic table on the wall that is complete. It has all the names up until the very last one, the bottom right corner. Okay. All right. I have a video of the periodic table, which I won't show you because of copyright. You don't need to see that. I think I showed you in grade 9 anyway. Okay, let's move on. Metals versus nonmetals on the periodic table. So the periodic table is divided into two main sections. On the left, the vast majority of them are metals. On the right, you have the nonmetals, and in between them, you kind of have in between, like metalloids, half metals, half nonmetals. And there are some properties pertaining to metals and nonmetals. So for example, of metals, a nickel. A nickel's a metal, and a non-metal will be like a bromine or oxygen, carbon, like helium. Those are all non-metals. So metals typically are solids. Okay, the only liquid metal at room temperature, meaning 25 degrees Celsius, that metal is liquid, is mercury. Okay, and I don't have that because mercury is dangerous. But if you do, because I've seen mercury in a bottle in a lab when I was working somewhere else, I was really startled. Wait, you have this in the lab? Like, bro, and you eat in here? So yeah, no, mercury is quite dangerous. It's a neurotoxin. Yeah, that's a liquid. That's the only liquid metal. Okay, all the other metals are solid at room temperature. So you've grown up and are accustomed to the fact that metals are solid and shiny. Okay, and all metals are shiny. They're bendy, meaning malleable. You can turn metals into thin sheets. You can take a hammer and whack them until they're like a sheet of paper. And of course, metals conduct electricity. We use them in wires, but non-metals, it's really hard to group them into one category because they're so different from each other. They can be solid, liquid, or gas. Depends on what you are on the periodic table. So that's why the periodic table is sometimes color-coded to tell you whether it is solid, liquid, or gas. The luster of nonmetals are usually not shiny. Nonmetals are typically dull. Think about coal or ice. Ice is a compound, but still made of nonmetals, and it's not shiny. It's transparent, but not shiny. You can easily break metals. Okay. When I use the word easily, I don't mean that you can physically easily break it. Some of them are pretty hard, but you can still break them. For metals, it's hard to break because it will just bend. If you take a hammer and you smack something made up of metal, it's probably going to bend and not break. Whereas if you smash something made up of non-metals, it's going to shatter into pieces. It's not going to change shape. Okay, and also non-metals are typically not great conductors, so they're insulators. Again, typically, not always. So here are some properties between each of these categories. Just know the general gist of this. Most of this, just think about a substance in your head and just describe that substance in your head, and you can pretty much answer these questions. You don't have to memorize. So the periodic table here is a typical one. Now this one is complete. Okay, every single element is named here, so this is the updated one. The first column down on the left in green are the alkali metals. Notice that hydrogen, the first one, is not included in that column. Hydrogen is not a metal, it's a gas, but everybody else down that column are metals. Okay, so they have a name, alkali metals, group 1. And then group 2, the one beside it, alkaline earth metals. Okay, kind of similar to alkali metals, but they have different properties. We're going to skip everything in the middle and go to the second last one, group 17. Going down the list, you have the halogens, the deadliest of nonmetals. And then the last column, you have the noble gases, group 18. Those 4 columns are the only columns that have names. We also call them families. The other columns, they don't have names. We just refer to them by their number, like group 13, group 14, group 15. They don't really have a name, but these guys have a name. You need to know their names. You need to know the members of that column and their chemical properties. Why do they have names? They have names for a reason, because they have special predictable properties, and they're all very similar to each other. All right, so any questions so far? All right, so here is something really important. Okay, this is the foundation for all of chemistry, atoms. Okay, everything is made up of atoms. Everything in this universe that we interact with, they're made up of atoms. Okay. Now, what's inside an atom? Because in Greek, the word atoma is a Greek word. It means indivisible. I mean, you can't divide it any further. That's actually false. You can definitely split an atom. That's how you get an atomic bomb. And scientists have repeatedly done that. So once you break the atom, what do you have? What's inside the atom? Well, if you look at the picture, you have 3 things. Okay, you would have protons, you would have neutrons, and then you would have electrons. Those are the 3 subatomic particles. Subatomic, smaller than an atom. Right, and in that table, let's organize protons, neutrons, and electrons. They have different properties, they have different mass, they're found in different places. So protons are positive. If you look at the picture, those red circles with the plus sign, those represent protons. Neutrons are neutral, hence the name neutron. Get it? Because it's neutral, it doesn't have a charge. Those gray balls in the middle, in the nucleus, those are the neutrons. The electrons are negative. They're not in the nucleus. Instead, they are surrounding the nucleus on the outside. And those little blue negative balls around the nucleus, those are the electrons. We don't like to write the words for proton, neutrons, and electrons because they're too long. These things show up everywhere in chemistry. So instead, we use abbreviations. Protons, just the letter P with a plus sign. Neutrons, just the letter N with the 0. And electrons would be the letter E with the negative. Okay, so if you see these symbols, that's what we mean. Protons P, neutrons N, electrons E, and then with their respective charges. So like I said before, protons or neutrons are in the nucleus in the middle, whereas the electron is in orbits around the nucleus. This is vitally important. Do we have any questions? Atomic structure. We're good. Okay, you need to know what these three words mean. If you learned it in your country, in your language, you need to know the English version of that. Okay. All right, so on the periodic table, we organize them by atomic number. So we number them from 1 to 118. What do these numbers mean? How do you get assigned a number? It is not the order that they are discovered. It is their mass. Okay. Atomic number tells you how many protons the atom has. If you have 1 proton, your atomic number is 1. If you have 7 protons, your atomic number is 7. Okay, so basically that's counting atomic numbers. Atomic mass is different. On the periodic table, you probably see 2 numbers. One of them is likely to be found on top in a corner, 1, 2, 3, 4, 5, 6, 7. You can just go down the order. But the other number is usually found on the bottom, like in the picture here, 4.003. It depends on the periodic table. Some of them gives you 1 decimal place. Some of you gives you 2. Some gives 3. In this case, that one gives 3. What is that? That's the mass. That's the amount of protons plus the neutrons. Okay, you need to know the difference here. So the protons are the red plus signs. That is the atomic number. The protons will define the element. So how do we know whether we're dealing with helium and not something else? Well, how many protons does it have? 2, then you're helium. Not 2, you are not helium. It's that simple. That is like their fingerprint. Okay, that's like their DNA, their ID. That identifies the atom. All atoms with 2 protons are helium atoms, no exceptions. If you don't have 2 atoms, if you give it if you don't have 2 protons, if you add another neutron to the helium, that's not helium anymore. Okay, but the mass, the mass is equal to protons plus neutrons. You can have different numbers of neutrons and still be the same thing, helium. That doesn't matter, but the protons has to be a very specific number. And we arrange the periodic table from 1 proton, 2 protons, 3 protons, all the way to 118 protons. That is the largest known element so far. And atoms on the periodic table are neutral. Protons are positive, but electrons are negative. They cancel out. Okay, if you have 5 protons, you would have 5 electrons, so that they cancel. You have a net charge of 0. So atoms are neutral. Unless something happens to disturb this balance, atoms are otherwise going to be neutral. Is that clear, everybody? Okay, so here is the review for Bohr-Rutherford diagrams. When I taught this to grade 9s, let me just drink some water. Yeah, when I teach it to grade 9s, usually there's a lot of issues. Okay, there's a few rules that you have to follow when you draw Bohr-Rutherford diagrams. And by the way, Bohr-Rutherford diagrams are just models that we use to represent what atoms look like. Okay, so I'm going to, in detail, show you how to draw one properly, because a lot of even textbooks get it wrong. Okay, it's not fair to call it wrong. It draws Bohr-Rutherford diagrams inaccurately. So you start with the nucleus. You have to draw the nucleus. You draw a circle for the nucleus. That's it. That's the nucleus right there. Inside the nucleus, it depends on what you're drawing. In this case, we're drawing calcium-40. Well, how many protons do calcium atoms have? If you just look on the periodic table, element number 20 is calcium. Okay, that means you have 20 protons. If I'm drawing calcium-40, the mass is 40. I have 20 protons. Well, the other 20 must have been made of neutrons. Protons plus neutrons gives you the mass. So if I have 20 protons, then I must have 20 neutrons to make 40. So you put 20p and 20n inside the nucleus, telling me what's in there. Okay, many people forget that. Many people are lazy and they just don't want to do that. So I asked them, so where's your nucleus? They're like, yeah, no, I'll do that on the test because I'm just practicing in the notes. On the test, they forget. Okay, so now let's fill out the electrons. Calcium 40, because it has 20 protons, it's going to have 20 electrons. They're usually equal. Well, how do you do that? Does anyone remember, before I show you, how do you draw these diagrams? What are the rules pertaining to electrons? Anyone?
2 on the first ring, 8 on the other ring.
Exactly. The first orbit, the first ring, that one, you can only have a maximum of 2. If you have 2, then you're done. You go to the next ring for the third one. It is full at 2. So we need to have 20. So here's 1. Here's 2. Okay. What do I add the third one? Well, I got to start a new ring. I know physically there's still a lot of space around that ring, but no, that's just a representation. Atoms wouldn't be able to have that space. Okay, and so hence, if you want to continue, you got to start a new ring. So 3, 4, wait, what? Look at how I'm doing this. Okay, so that's what I mean by you got to do this properly. It doesn't matter if you go clockwise or counterclockwise. I like clockwise. I'm just going to go clockwise. Go 1, 2, 3, and 4. Okay, you don't pair them up unless you absolutely have to. Okay, there are 4 spots like in a clock: 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. You don't want to pair up with somebody unless you have no space left. Like there's social distancing from each other. We are social distancing now because of COVID. We don't want to catch it from other people. Electrons naturally hate each other. They don't need COVID to hate each other. They're all negative. Negatives hate negatives. They don't want to be close if they don't have to. Okay, so they try to space themselves out. So the first 4 are going to be spaced out. The 5th one, yeah, you have no choice. You ran out of spots. You have to share. You have to be close to the first one. And then the next one is there. And then you just go around in a loop for a total of 8 in the second orbit. Okay, so first orbit has 2. The second, the maximum capacity is 8. Okay, any questions? Okay, so we have 10 so far, 2 plus 8. We need 20, so we got to start a new one. And the next one, the maximum capacity is also 8. So you go 1, you start from the top, and then you will go clockwise again. You go 2. Again, you don't want to pair them unless you absolutely have to. Okay, so 3 on the bottom, and then 4. And then, of course, you would go 5. Now you pair them up because you run out of space. Electrons don't want to be paired unless they absolutely have to. And go 6. And then 7 on the bottom. And 8 on the left. And that is the third orbit. So now you would have 8 in the second one, 8 in the third one. So that's a total of 18. Again, calcium has 20 electrons. So you got to have 2 more, meaning that you have to start yet another orbit and just add the 2 electrons. You go 1 and 2. Okay, do we have any questions? Anybody? Seriously, you're not going to ask me why they're separated, why they're together? No? How come, so I have a question for you then. How come the orbit on the outside, those 2 electrons are separated, but look at the inner orbit. Those 2 electrons are together. Did I just do that by accident? This is willy-nilly, or is there a reason to that? What do you think? Okay, no one knows. I don't know how you learned this in grade 9, because here's my little rant about the textbook. In some textbooks, for the first ring, those two electrons are separated. One on top, one on the bottom. Okay. In fact, I think your textbook has that as well. That's technically inaccurate, because in the first orbit, the electrons, they have to be together. They have no choice. Okay. Just like all the other electrons, they're paired up. You see what I mean? The first orbit has to be paired. But that last orbit on the outside, they're not paired up, because you have 4 spots. You can have a total of 8. So they're going to want to occupy different desks, just like you guys. If you go back to school, you probably want different desks. You want to sit beside somebody right now. Electrons never want to sit beside anybody. So that's why they are separated. The first orbit, you have no choice, because you can only have 2 electrons. So they have to be together. Okay, so that's the reason here. You need to know how to do this. Okay, so here is a practice page. So please draw one into your notes, and I'll give you around 5 minutes, and then I'll take this up. So actually draw that, because that will be on the test. All right, so I'll take 5, and I'll come back in 5. Okay, anyone encounter any difficulties? Because I can't see what you're drawing, so I don't know. Do we need to write anything in the nucleus? Yes, you do. In the nucleus, let me just go back. Look what I have on this slide. You need to tell me how many protons and how many neutrons. Okay, don't just draw a circle. That's what a lot of people do. And a lot of people draw a circle and they put the element symbol, like for this one, calcium, Ca, in the nucleus. You can't do that. You have to tell me how many protons, how many, neutrons. All right, I'm gonna take this up. Okay, you can't actually type your model into the chat, so compare yours with mine. And if you're not finished, that's okay, because we do need to move on. It starts off really easy. H1, just hydrogen. That is the easiest one that you can get. That's it. It has 1 proton it doesn't have any neutrons. Look, the mass is 1 proton. Okay, that's it. 1 electron, so 1 circle and a dot. It doesn't matter where you put the dot. Anywhere along that orbit is fine. Helium is the next one. The atomic number for helium, what is it? Into the chat, please. Two. All right, yeah. So if you just, again, you're not supposed to memorize those. Looking on a periodic table would tell you that it is 2. So helium atomic number is 2, meaning that you would have 2 protons. Since the mass is 4, the other 2 missing must be the 2 neutrons. Okay, so 2 protons, 2 neutrons, you get 4. And then helium should have 2 electrons because the charges have to balance 2 protons with the 2 electrons. So that's what you would have. Still in the first orbit. Okay, so with lithium, that would be the next one. You would have 3 protons. That's atomic number of 3, meaning that you would have 3 electrons. Notice that I'm starting a new orbit now. The new orbit, because that first orbit is full. You can only have 2. And then 4 neutrons. 3 plus 4 is 7. It says lithium 7 in the question. So atomic mass is 7. 3 protons because it's lithium. What's missing? Well, 4. And the last one is the hardest one. If you haven't got to this one, no problem. Fluorine, if you look on the periodic table, again, protons is 9, neutrons is 10. Okay, how do I know the neutrons is 10? Because the question says fluorine 19. So the difference must be 10. And of course, you would have 9 electrons, and you would draw the first 2 in the first orbit, 7 in the second orbit, and look how they're paired together. Okay, you have to pair them together. You can't just randomly draw those dots in different places. They must come in little groups of 2, and one of them is single. Okay, you might think that's kind of upsetting. Yeah, fluorine really wants to get a partner for that electron. In fact, fluorine is the most reactive non-metal. It is so desperate to get another electron for that, it will react with just about anything. Okay, so that's how you would draw these diagrams. Please make sure you practice. You might miss certain things if you don't. Okay. So now we come to electron arrangement. Okay, so still review of grade 9. If you look down a column on the periodic table, you can see that they are going to be very similar. Okay, you're going to have similar structures. So if you look at the picture on the right, you have the noble gases. How do I know they're noble gases? First of all, they say helium, neon, and argon. I remember those are noble gases. And look at their outermost orbit. They're completely full. So helium has 2 electrons. It doesn't need any more electron. It's already full. Neon has a perfect 8. Argon has a perfect 8. So these elements are very fortunate and privileged. Okay, they are born without a need for getting electron. Those are like the people born from rich families, extremely rich. They don't have to work for the rest of their lives. They're just born into privilege. You said you can go clockwise or counterclockwise. Doesn't matter. Yeah, it doesn't matter where you put the first one. Clockwise, counterclockwise, you do you. All right, so these are the noble gases. So for that reason, noble gases are quite chill. They don't do anything. Okay, they don't react with any other elements because they don't need to. Okay, does that make sense? They're already stable with an outer full shell. Now, the other atoms on the periodic table, they're not born into privilege. So they need to work. They need to do stuff in order to fill their outer shell with electron. They want a full outer shell. So they have to do things like reacting with others, stealing electrons from others, sharing electrons from others, starting a communist government and have all the atoms share everyone's electron with each other. Okay. That's not a joke. That actually happens in atoms. So therefore, they need to react with other compounds in order to achieve a full outer shell. Yeah, that's the idea of ionic and covalent bonding. Okay, so we're going to only learn about these two, ionic versus covalent bonding. There are other types of bonding, but that doesn't concern us. So they will have to join up to form a compound. So individually, yeah, they need a full outer shell. So they find a partner, they make some deal with that other atom so that they both end up having an outer shell. Okay, does that make sense? Okay. On the other extreme, okay, noble gases are on the far right of the periodic table. On the far left, the alkali metals. Yeah, they have one pathetic valence electron. Only one electron on the outside. They need a whopping 7 to complete it. They're not going to do that. Okay. Instead, they kind of go about this the cheeky way. They cheese the system. Yeah, you want a full outer shell? No problem. I'll just get rid of that one. And the inner shell now will become the outer shell. So I have a full 8. That's what they do. Okay, so alkali metals, they are also very, very reactive, just like fluorine is. Fluorine is extremely reactive because fluorine, as we just drawn the picture, it has 7 valence electrons. I just need one more. Please give me that one more, just one more. Okay, so that is very desperate. So when you're having a collection, you're just missing one thing. Yeah, you're going to be very desperate for that last piece of the puzzle. Okay, so fluorine is reactive because it needs just one more. But these guys, they're also extremely reactive because they just need to get rid of one. Okay? They don't want that to come home. You're a shame to the family, get out. So they kick out their only valence electron on the outside so that they have a full outer shell. So they get disowned. And because they're so violent and reactive, they will violently react with water. Okay, if you drop an alkali metal in water, you better be prepared for whatever is about to happen. It depends on how much you dropped and what you dropped. If you drop a tiny piece of sodium, you're going to see some bubbling and swimming. It's all going to be fun. If you drop a large chunk of sodium, prepare for an explosion. If you drop a large chunk of a heavier alkali metal down the table, yeah, prepare to die. It depends on what kind of safety precautions that you took. Okay, so in fact, they're so reactive, you're not supposed to touch them at all. Because if you were in my grade 9 science class, we kind of played around with that. And I cut a piece for you. I didn't trust you with the sodium. Oh, no. I had to cut one for you. And I used tweezers to give it to you. I wasn't going to pick it up. Okay, because it actually does hurt. It will react with the sweat on your hands. If you're not even sweating, doesn't matter. There's water in your cells, and that will scar and it will hurt. One time at my old school, we put too much potassium in water, and it was bad. Yeah, I can pretty much guess what happened. There might have been an explosion that destroyed the beaker and splashed things everywhere. Don't ask me how I know that. Yeah, okay, I see what your school did there. Yeah, potassium is even more reactive than sodium. Sodium typically won't burst into flames unless you have a big piece. Potassium will always burst into flames. Okay, so yeah, these guys, you really don't want to mess with alkali metals. Okay, they're reactive because they don't need to do much to achieve their goal of having a full outer shell. Just get rid of one electron, just one. It's easy. Okay, if you want to sell chocolate at the mall, you only need to sell one. Yeah, you can get that done pretty quickly. If you have to sell a whole box, that's a different story. But selling one is easy. So if you move down the group, like I said, lithium down to sodium, down to potassium, the further down you go, the more violent the reaction becomes. Okay, because the bigger the atom, the farther away that electron is from the nucleus, so the less attracted it is to the nucleus, so it's even easier to get rid of. If you want to disown your child, it's kind of hard when they live with you 24/7. But if your child is on the other side of the planet, it's really easy to cut them off. Very dark example, but you know what I mean? Like, you can just cut off someone really easily if you're not close to them, like physically. I have a copyrighted video, so I'm not going to show that yet. I'm going to show you after. So let me just summarize everything here. So what we learned today, we learned about chemical versus physical properties. We learned about what elements are, what atoms are, what's inside of atoms, proton, neutrons, and electrons, how to draw Bohr-Rutherford diagrams, how to represent atoms, and also reactivity of atoms. Okay, so I'm going to stop the recording.